My name is Jacek Śmietański, and for the last 3 years I was working for DTIQ, mainly with a project that was funded by NCPR. So it's a research project applied to the needs of the company. Actually, I was working for DTIQ until yesterday. That's why I changed my email, and you can see on the slide the new one, as I'm starting new position in Cisco with new innovative project. But today I will talk mainly about reidentification. If you were last year on ICON on my talk, I was talking about loss prevention in AI. This talk will be rather continuation those from last year. What more? This will be rather use case. So I will present our experience and challenges that we met during realization of this project. Do not expect from me a bunch of code. Actually, here will be no line, even no one line of code. Rather, you will see a set of videos with examples. Do not expect from me a deep dive into the identification topic with details on each algorithm, etc. I would rather present our thoughts, our experience. Okay, works. Okay, something about me. Privately, I'm a big fan of geocaching, so you can find me with nick Dadoskawina. And also I do collect tickets. If you go here to Gliwice by bus, by train, and do not need to return the ticket to your worker, you can feel free to give it to me. Each used ticket I will take with thankful. If you visited something interesting in Gliwice and have spare ticket, the same. The end of advertisement and going to the topic. DTIQ company works for QSR industry. That means quick service restaurants, so McDonald's, Burger King, Subway, etc., etc. Those are our clients. Most of clients we have in Spain and in the USA. And what we do? We identify anything that is out of, not expected, out of normal. So, for example, some frauds, for example, unexpected behavior. During last year topic, I talked about tables cleanliness checking. So we monitored if the table is cleaned fast enough when the client finishes his eating, etc. I will now concentrate on the speed of service project. This means that we analyze video material from cameras that is, for example, over the location, and we count people inside, we count people waiting for their order, and we try to assess how long they are waiting. So, of course, if they are waiting too long, it should be reported. Okay, first video example. So we are working with views like this. So A panoramic camera located on the ceiling with a view on the whole inside of restaurant. Okay, so we can see the area where people are working, so they are taking orders, they are preparing those orders and take them to customers. We have area with tables where customers eat, and the most interesting for this case area is this area that is marked by red polygon. That is area where people are waiting for their order. So at least we are sure that it's true. As you can see, there is no standard queue. So people are staying, walking, etc. during the whole area. So the idea is just to count number of people inside this polygon area and then divide this count by number of orders that were taken, so we can estimate mean time that each people wait for order. You can see many issues and disadvantages of this solution. So, for example, people can come in group, and a group of people can take only one order. People can go with children. Children, for example, can be in a roller. So there are also problems. Restaurants can be overcrowded. So people can be one by one. It may be hard to distinguish one from the other, etc. One more example. Here we have on the middle of this polygon area we have something like luggage, possibly, that is constantly misdetected as a person. This take too long, very long time, so finally lead to increase the error in detection. You can also see that this view is not optimal. That is the philosophy of the company. We want to prepare those installations with the lowest cost. So we assume that restaurants like this don't want to spend millions of dollars for very accurate, very new cameras that will be in ideal place. So we are using those cameras that already existed here. So sometimes we have views like this. So you can see at the bottom people are cutted, so we can see only legs. They are sometimes detected, sometimes no. Okay. How improve this process? Of course, we can add new data and retrain the model with new data, better model. Possibly the model will be better, and this is done on a regular basis. We can optimize zones, so the polygons that determine the area that was when detections are counted. It is possible, but very hard. It should be done individually for each location. Currently we have over 700 locations deployed, so it is a huge work. And of course, that should be a specialist who know how correctly select those zones. It is also problematic. We can try to develop videos. The warping is the idea of changing panoramic view to something more classic. So there is a mathematical equation that transform the view, the original view to the warped view. You can see that it somehow possibly make this view better, easier to detection model. We tested it and we got some improvement with parameters that were currently that time on production, but later we realized that we can just simply adjust and optimize those parameters. So we got better results just with parameters, model parameters optimization, without need to go to such, introducing this solution is very costly and could not be done just like that. So finally the warping was rejected as not a good idea. We had an idea to combine head and body detection. So the source of the idea was that we sometimes detect only head, sometimes only the rest of person, and maybe if we try model that will detect both of those classes and combine them, we got better results. We tried it, and no, it didn't work as expected. We got good enough results, but not that better to invest in changing the whole infrastructure. So maybe enable real-time inference and add tracking. There is one thing that should be mentioned, that the solution doesn't work in real time. That's because we need to run it in a very limited environment. So it's the same history as for cameras. So we don't want to expect from client to invest millions in clusters, etc. So we want we expect the solution to work on simple edge device or other PC. The same device should also monitor other aspects. So doors, entry to. We have entry-exit project that measure number of entries and exit by doors to the restaurants. We measure drive-through, so outside, and all of these should be concurrently calculated on this device. That's why actually the measure for speed of service are taken in 10-second snapshot. So one photo per 10 seconds. Then we do object detection and calculation. That's why we are unable to introduce tracking to this project. Example is from our project, but not from service in-house, just because, as I said, we didn't try poor tracking for this project. But you can see how tracking should work. So each detected object should be individually identified. So for each object, ID is assigned, and you can see that this solution doesn't work perfect. For example, for those white cars on the top of the image, sometimes the ID is changing. For example, if some people pass by before this car, but for this solution it's good enough because we are concerning only of this area marked with rectangles. Anyway, for tracking we meet some problems, some challenges. Tracking is based
Troszeczkę bliżej, prawej strony. Bliżej tutaj.
Okay. Tracking is based on previous results of object detection algorithm. So, if object detection algorithm fail, also there is no object to track. Misdetection, missing detection, this also influence the tracker. Occlusion and grouping. So if interesting object is occluded by other object, it may not be correctly detected. The same for groups. If we see groups of objects in the same place, they can be detected as single object. This problem is not that important in car detection, so you can see that cars are big and it's a small chance that two cars are grouped, but for people inside it's the other story. So we cannot use tracking for SOS inside, and so maybe use reidentification. And now going to the clue, we tried how reidentification will work for our problem. The identification problem itself is quite similar to tracking, but it's more general. So in tracking we require that we have real-time detection, and then we calculate, for example, distance that object was moved from since the last measure, since the last occurrence. In reidentification, we don't assume real time. We even don't assume that we have view from the same camera. So we can use reidentification on any view. So I can have one camera here and second camera outside of the building, and I can check if a person that is here is going out from the building and can measure the time difference, for example. This generalization, of course, imposes that the reidentification problem is a bit harder than simple tracking problems. In general, identification problems are solved by measuring distances between two images that should be compared. We have, in imaging, we have a set of objects detected in one view and a set of other objects detected in the second view. And we want to assess if both views have common persons. So we need to compare each person from the first view with each person from the second view and calculate distance between them. And those persons that have the minimum distance, the closest, are considered the same. So we have two questions: how we calculate those distances, and what is the threshold? Which value of distance can show us that those people are the same or that those people are different? And those answers depends on the case we want to solve and on the algorithm we are using. There is a bunch of algorithms, reidentification algorithms. In the major cases, they are working as a convolutional neural network. So something similar to object detection network, but this is the other network. So if we want to do reidentification, we actually run two networks. One model for object detection, and then the second model for reidentification. This also involves that we have the computational cost increases. And may increases significantly because reidentification time may be longer than object detection time. In object detection, we look for one image, and using YOLO or something like this, it is pretty fast. With reidentification, especially if we have to compare a bunch of set of images, it may be time-consuming. Here is a list of algorithms that we tested for this project. I cannot say that those algorithms are the best, and I cannot recommend any of them. Why we choose them? There were two reasons. First, we were limited by NCBR project, so some of algorithms were explicitly stated in proposal, so as proposal was accepted, we needed to test them, regardless if the proposal was written a few years before, and not necessarily those networks are up to date. And the second one was the implementation quality. So starting those projects, all of us had zero knowledge on re-identification topic. So all of us did research. We were looking for good implementation that can be applied with a minimal cost. So we were looking for algorithms that works with our code, algorithms that we can understand, code that we can understand and somehow incorporate to our repository. So, finally we choose ReID++, ReID and ReidMBM. As I told, I don't want to go deep into those algorithms, but to slightly show the difference between all them. Aligned ReID divides somehow image for parts and try to align each part separately. Each algorithm, regardless of the way it works, finally produce something like this distance map. So a big number of features that are extracted from each analyzed image, and based on those features, a simple scalar is calculated that means distance. So it can be just simple Euclidean distance or something like this. The second algorithm uses standard convolutional network, but it adds to it something like spatial temporal statistics. And authors says that it improves detection. The third network, ReidMBM, Lightweight Multi-Branch Network, is quite similar. It also creates more than a single network and then combine results. Okay, we implemented, we took those code from GitHub, implemented it, adjusted somehow to fit to our code, and then we started to train models. But before training, we need data. And here we make a fuck up because we requested data in very detailed fashion. So we thought that each person should be in details described. So it should be information if the person carried backpack, carried bag, carried handbag, so different types of luggage. We needed to know, we wanted to know cloth, the color of the cloth, upper, lower, the length, if the shoulders long or short, and etc. etc. If has a hat, we have noticed that some of people know hold hats, so it we request that it should be attributed. And we got from annotation team data set with detailed information. I said that this was unnecessary because as it finally occurs, such input doesn't fit to any of algorithms that we found. So we had two possibilities. Either do big refactor and somehow change the way how the algorithm works. It was a huge work. Either just throw away all of those attributes. So to justify why we collect data before doing deep research and making sure that such data will match to our code. So annotation data is a very hard work and time consuming. So if we do request for example, 1,000 of images annotated, we need to assume that we don't get it not earlier than, for example, the next month. So we requested it without proper advance. So there is a bunch of publicly available data sets, so all models are pre-trained on those. We actually use train models with our data set, but we decided to stick to original implementation, and data we provided were in the same format as in original market 1501 data set. This number is that in this data set means that in this data set 1,500 people are annotated. This data set contains views from 6 different cameras, and of course the same people have the same ID, different people have different IDs. Okay. We applied the solution to our problem. So we tested each of those algorithms. The results were so-so. So you can see the ID of detected person is represented by the color over the bounding box. You can see that sometimes the same people change the ID, so it is not working as expected. Additionally, those errors can be very large, not only because not ideal re-identification, but also because we assume too ideal behavior of clients. So we assume that a client will first go to the green zone, then in green zone he take an order, and then he will wait in the yellow zone. So we assume that he doesn't go out of the yellow zone, and then he go to the blue zone and to receive the order. It is not exactly true, and this need to be adjusted. Going to the second topic, drive-through in outside. So problem is the same. We want to detect each car or each vehicle, because that are not only cars, sometimes some motorcycles, buses, etc. And we want to detect each vehicle that is taking order and count the time between taking and receive the order. Here we have a quite different situation. We have a different view. Here is a standard view, and we have 2 different cameras, because usually one single camera cannot show both places. On the left you have a place where driver where driver takes an order, and on the right the place when the food is providing to him. So here is the case when reidentification is a natural solution because we have different views. And the question is why? Do we need reidentification at all? Because, so, it's obvious that first car is going to the menu board when he tells what he wants to eat, and then to pickup board. And here we have, you see, standard queue, so no problem, I think. So we'll detect here car here, detect car here, and we should be able to estimate time of waiting for each car individually. Yes, sometimes it works, but there are different architectures of drive-through location. So there are common situations where we don't have a single menu board, but there are more of them. So car can go not from single queue, but from 2 or more queues. Sometimes happen that if, for example, order is more complicated, that car goes out from the queue and wait for it on the parking or something somewhere here. And those cases have impact to the final results. So here we introduce the identification, but not as a base solution, rather to improve decision in problematic situations. I can say that this kind of reidentification for this problem works better. It really improved the final outcome of drive-through. Here you have example how it works. When car enters a menu board, it is registered, and the image of detected car is stored in the memory. And when car reach pickup point, all images of cars that were previously at menu board are compared to the view from pickup. So one thing, views are there is no so many such views, so it doesn't significantly slow the whole process because we usually need to compare 2, maybe 3 or 4, 5 cars, not so much. When a car is matched, they are removed from the memory and not considered for further re-identification cycle. And using this solution, we achieve improvement. I think from 92 to 97% of. Actually, drive-thru solution works quite good. It is much easier than detection of people in very crowded restaurant. basically all what I prepared for you. Here is the team who worked with me with this project, especially Dominik team and Karolina Sikora were involved in a reidentification process.